Hi, thanks for joining me. Today I've got another non-standard proof for you. I'm going to be proving Fermat's little theorem, and as I say, it's not going to be the standard proof. Now, in fact, I've already made a video in which I prove Fermat's little theorem, and that video as well is also a non-standard proof. This one's different, of course. I'll leave a link to that one in the description below. I use graph theory to prove it in that one, but this time I'm going to be using a completely different trick, and again, it's not the standard one. Firstly, let me state what Fermat's little theorem is, and then we'll get straight into the proof. Okay, so if we have p a prime number, then a to the p is congruent to a mod p for any non-negative integer a. So you may have seen a different formulation of Fermat's little theorem where it says that a to the p minus 1 is congruent to 1 mod p, but that requires that a and p are co-prime. This does not require that a and p are co-prime. So simply a to the p is congruent to a mod p for any non-negative integer a. Let's get stuck into the proof. Okay, so the first thing we need to do is quickly state and prove a lemma. I claim that if x and y are any non-negative integers, then x plus y all raised to the p is congruent to x to the p plus y to the p mod p, where p is our prime number from before. Let's prove this. The proof is not too difficult. We're going to use a binomial theorem. So x plus y to the p, well, we know that that's by the binomial theorem, x to the p plus p choose 1 times x to the p minus 1, y to the 1, or just y I should write, plus so on. Let me write the last two terms here. Then p choose p minus 1, x to the 1 times y to the p minus 1, plus y to the p. So we've got our x to the p and y to the p. Now I claim all this middle stuff, so all of these middle terms, when I add them up, I'm going to get a multiple of p. And I do that by firstly claiming that p choose I is a multiple of p. So for I between 1 and p minus 1, I claim that p choose I is a multiple of p. And to see that, what is p choose I? That's p factorial all over p minus I factorial. And now we know that this thing here is an integer. But now notice we've got a p, if we expand the top, this is p times p minus 1 times p minus 2, and so on, down to 3 times 2 times 1. And on the bottom, we've just got p minus I factorial times I factorial. Now, the thing I want to highlight is we've got a p on the numerator here, but on the bottom, we do not have a p. And the reason for that is p minus I, because I is at least 1, p minus I is going to be strictly less than p. But because p is prime, no number less than p has a factor of p, okay? Or shares any common factors with p. So when I do p minus I factorial, that when I expand that out, that's not going to have a prime factor of p. Similarly, because I is less than or equal to p minus 1, the same argument applies. When I expand that out, that's not going to contain a prime factor of p. So if I sort of look at the prime factorization of the bottom, there's not going to be a p involved whatsoever. But because I've got a p on the top, there's nothing to cancel out on the bottom. That means the result, whatever I compute this to be, will always be a multiple of p. And that kind of proves the lemma, because I know that this thing here, p choose I now, I know is a multiple of p for any I between 1 and p minus 1. But notice that includes p choose 1, the next term which is p choose 2, and so on. So all of these middle terms here are multiples of p. So when I add them up, they're of course going to be multiples of p as well. So when I look at this thing here, let me write it here, that's just going to be congruent to x to the p plus y to the p mod p, because as I say, the middle terms there are multiples of p. Okay, and that proves our lemma. Now let's get on to proving Fermat's little theorem. Okay, so now we're going to prove Fermat's little theorem, and the way we're going to do that is by induction. So let's look at the base case when a equals 0. So then we have that 0 to the p, well that's just 0, and of course 0 is just congruent to 0 mod p. And that's the base case done. It's quite straightforward. We have that a to the p is congruent to a mod p in the case a equals 0. So now what we're going to do is assume that it holds for some a equals k. So assume k to the p is congruent to k mod p for some k in the non-negative integers. And now what we want to do is show that this also holds for k plus 1. And we're going to use our lemma. So k plus 1 to the p, okay, by our lemma, that's congruent to k to the p plus 1 to the p. But of course 1 to the p is just 1. And now by assumption from this thing here, k to the p is congruent to k mod p. So we've shown that k plus 1 to the p is congruent to k plus 1 mod p. And that is the inductive step done, because we've shown it's also true for k plus 1. In other words, if we have a equals k plus 1, a to the p is congruent to a mod p. And that's our proof by induction done for Fermat's little theorem. I hope you have enjoyed this video. Thanks for watching. I'll catch you in the next one. Have a great day.